my tribe, where I came from, and databases, and sort of how what the intersection of databases and all the stuff we've been studying in distributed systems is. It turns out that there's a lot of neat commonalities, not only for the obvious reason that for practical reasons to make databases go fast, they tend to be distributed nowadays, and it'd be harder to write and maintain for all the reasons we've been studying in this class. But apart from that, sort of the notions of what it means for a program to be correct in terms of having this illusion of there not being distribution or concurrency and so on, it's like really, it turns out is really, really similar in the database world to what we studied in distributed systems. Although we're going to have to introduce a bunch of different terminology to understand how that mapping actually works. So I want to talk, and then I think the other thing that's interesting to talk about databases is that in our last class, we sort of began to look at the concept of consistency in a more nuanced way. We said up until now, we set this one kind of standard for consistency. You can't tell the system is distributed. You can't tell the system is replicated, right? And then we began to say, no, that's a lot more nuanced than that. You can have a lot of different levels of consistency. And there are a lot of interesting levels of consistency that are strictly weaker than strong consistency. I talk about when I say strictly weaker, I mean precisely that if this is strong consistency, they contain executions that are not strongly consistent, as well as all the ones that are. You should have this intuition that by permitting more executions, you might be able to be more available, you might be able to go faster. Like, there's a reason why you might want to be out in this space, but there's a reason why you might not want to be. It's just a sort of trade-off between, I want my system to be really easy to reason about, I want it to be strongly consistent, but I might want my system to be fast and up, and it might be easier for me to build. What's interesting about databases is that in databases, we get notions of consistency that are strictly stronger than what we call strong consistency. And we'll talk about that a little bit in this lecture too, I hope. Okay, so, but what is a database? What's a database? Who's taking a database class? Like nobody. Next quarter. What do you think a database is? Well, here's a question. How is a database like any different than the sorts of replicated storage systems that we've been studying all this time?
It can split data across multiple replicas instead of like having the
partitioning is what you're saying.
Yeah, if you want.
Yeah. So I don't think there's anything specific about databases about partitioning. It just happens to be the case that we haven't studied data partitioning in the context of distributed systems. It's going to turn out that that's sort of a cross-cutting thing that you could apply to a distributed storage system or a database. Any other, like, what else is different, right? So we've had this notion of we have these stores, and they store variables that are mapped to values, and we've always modeled them as sort of integers and strings, but they could have been something else. Yeah?
According to that, the key value store that you're doing has an database.
Yeah, I mean, I think in some important sense, the key value store is a database, right? When you talk about relational databases, it's usually not just a mapping of scalar values to variables. Instead, you have this concept of relations that are like tables. This is an employee table. And the employee table might have an employee ID and an employee name and a department that the employee is in and their salary or something like that. I don't know. So the idea being that you can kind of store this and say, like, a record might look like Peter, you know, he's in the CS department, and actually this is public information. I make $120,000 a year. Look that up if you're a CS professor. You can look up what all your colleagues make too, and it's totally weird. It's not weird, it's great. Transparency is great. I'm used to it where you're coming from. But anyway, the point is that the data can be structured a little bit more richly than we've seen. But that's not that important, right? It's also the case that in databases we typically have a much richer, what's called a query language. Right? So instead of just saying, I would like the value of the variable x, please, you might be able to write something like a little program that describes a bunch of transformations you want on the data. I want you to take all the rows from the employee relation whose second column is Peter, and I want you to join them up, right? I want you to join them up with the department relation so that I can figure out what floor I'm on, or something like that, right? So you can kind of construct a fairly complicated query. So that's one. So what's the first thing? The first thing is the data is more structured in terms of relations, but that's not really important, right? Because I could have put a row in the data stores we've studied, and then it would look structured, right? So that's not really fundamental. They have rich query languages in general, and they have this notion that we have not looked at at all of a special type of compound action called a transaction. Transaction is it meaningful for anybody? Does anybody have a sense of like what a transaction would be in a database? Or even what a transaction would look like in the sorts of key value stores that we've been playing with so far? Yeah?
The transaction is like a message, so to speak, or like that's the request.
Well, but if that were true, then we've already studied them,
Yeah.
right? So it must be something more than that. Yeah?
A series of writes like to the database that you would like as you choose to commit or like roll back.
Yeah, so there are two aspects, right? The first and maybe most important one is that transactions allow us to talk about multi-object operations, right? Like in a transaction, I might want to say, what's the example we've already looked at actually? I want to move money from one account to another. Well, there's no move primitive, but what you have is deletion and insertion. So I would like to delete from this thing, and I would like to add to this thing. Here's the problem. I need them both to happen. And that's not all. But so the idea is that transaction is a multi-object operation, and yes, it's something that like could fail, and you have this idea of it either commits in the sense of all of the operations happen, or it aborts in the sense of none of the operations happen. We studied commit protocols that can be used to enforce this in practice, right? But we didn't really talk about the programming model of transactions. Now, when I say that transactions are a programming model, what do I mean by that? What's a programming model? So Jim Gray invented transactions, and he did say that in his mind, they are a programming model. What on earth does that mean? What do I mean by that?
Yes, it's like a way we can model problems, perhaps in distributed systems, in a similar way to transactions are held in databases.
So a programming model is a way of modeling things. That's true. That's true. But it's a specific way of modeling things. Hey, Lindsay, how would you define a programming model? It's kind of a weasel word, right?
Yeah, you know what? I was asking a bunch of people on the TL in Slack, which is a Slack channel for programming languages researchers a while ago about what they thought a programming model was. Because I was having a really hard time coming up with any definition that was different from programming language.
So let me try. Okay, so I do think it's like a weasel word, like declarative. It's kind of in the eye of the beholder, or it depends what, it can operate at different levels of abstraction. It depends on what you're abstracting from. And this is sort of true with declarative too. Declarative means more abstract than that other thing we were just talking about usually. Yeah?
I was going to say maybe it's something with states and actions, and you can use actions to go to different states.
Well, that would be a model, a programming model. Yeah?
So this is Chris Martin's definition.
Good.
First she said programming models are cognitive tools for imagining computation.
Okay.
But then she said,
I would say that with and something else. That I would say that are exposed or reified in the programming language. Maybe via new primitives in the language, maybe via constructs that were layered on via libraries or something like that. But the idea is, it's a way of thinking about computation that is, in some sense, hoisted into the language. So you actually have things in the language that talk about the idea. Let me explain what I mean. Let's say I wanted to subtract $100 from X's account and also add $100 to Y's account. Okay, those are two operations though. I need to tell the system about my intent for the system to be able to do the right thing. I need to, if nothing else, tell the system, I need these two new verbs, if nothing else. Here's a verb that says, a transaction is beginning, right? This is the beginning of a transaction. And then you need to tell me where the transaction ends, because then you might do some shit to Z, but you don't care if it happens unatomically with respect to everything else. So you need some way of saying, this is the end of the transaction. You need this additional, and you can imagine adding transactions. This is what Jim Gray suggested to your favorite programming language. You can just a very simple programming language for bank accounts. And all it allows you to do is subtract and add things. It could be C, it could be SQL, it could be anything you think of, but whatever it is, you have to add 3 verbs. And I said close, but really you need the programmer to be able to say, please commit if everything went right, or please abort if everything didn't. So the way that it was manifested at first was there's this structured query language called SQL, and Jim Gray said, you should have a thing called begin transaction, a thing called commit, and a thing called abort. And by the mere addition of those 3 things, we can understand what people mean about what needs to be grouped together. Does that seem like a reasonable definition? Like it has to in some way not just be an idea, it has to be in a language.
Yeah, so I guess like the reason why I still didn't see the definition between the difference between that and programming language is big because I don't believe that a programming language is something that necessarily has to be run on a computer. So that makes me a weirdo.
That's fair. That's because you're,
So,
almost everybody except for people who are in the tribe of programming languages do think about programs as things that come out of the computer. That's awesome. Okay, so it is a programming model that allows people to do multi-object operations and enjoy some guarantees. Now, we maybe have an intuition about what the guarantees we want are, but let's be a little more specific. How many of you have heard of ACID? Not the drug, but rather the collection of guarantees. No, none of you, really? Okay, very few. Yeah, you've heard them. Okay, so what is a atomic? What do you think that sort of means with respect to this toy example over here?
All or nothing.
Well, exactly what I just said. Like, please don't leave the database in a state where the money appears to have disappeared or to have doubled for no reason. Okay? And we're not even going to talk about C, because even when these guys came up with this acronym, they didn't have a good definition for C. C means consistent, but it all means consistent, so forget about that. What does I mean?
Isolated.
Isolated. And so, like, what does isolated mean? And does it matter in the context of this toy example?
Is one transaction shouldn't have an effect on another.
Yeah, it's that one transaction shouldn't be able to perceive that there are other concurrent transactions with which it might conflict, right? We should have this illusion that from the minute that we begin the transaction, until such time as we decide to end it, we have this illusion that we're the only user of the database. We've locked everyone else out. Now in practice, we could implement that by literally locking everybody else out of the database whenever somebody begins a transaction, but that would not be practical, right? Because a slow user would stall everybody else and we'd have to have a lot of locking. So I want it to appear that I got a big lock without actually getting a big lock. And the reason I care is, like, let me give you a slightly different example to show why I care. Let's imagine that instead of moving data from one account to another, I was giving a bonus to two employees. So I said, like, X plus equals 100 and Y plus equals 100. And the fact that I put them in brackets says I want them to both happen or not. So that might be T1, transaction 1. But there might be this other transaction, which we're allowing to run concurrently so that we can go faster, which says something like this. X is X equals X times 0.006. It's an interest calculation or something like this. Right? And also the same for Y. Y equals Y times, or Y equals Y plus equals, sorry, Y times 0.006. So that's cool. So atomicity alone says that neither of these compound actions will happen by itself without the other one happening. But it doesn't say anything about a really nasty thing that could happen if we were careful about this. And I'll point out right now that it could happen even in a strongly consistent data store, like a key value store. So we could have done primary backup and done these things, and we would not get isolation. So isolation in the transactional sense is strictly stronger than strong consistency. Does anybody have an intuition for what the bad thing that could happen is? Yeah.
Is it transaction 2 happening before transaction 1?
Well, transaction 2, and I'm going to formalize all this stuff with ugly definitions in a minute. I want to do intuition now. That would be, in some sense, okay. For the same reason that where we say, like, Doris database is here, and there's a client 1, there's a client 2, and they both, at roughly the same time, with no causal relation between them, fire off a message. Well, there's two things that can happen. But either one of those two things is fine. Right? Because they could have happened when concurrent things can happen in one order or the other. So there's one world in which it's the happy world for everybody, in which you get to do the interest calculation after getting the raise. Woohoo! Everybody makes more money. There's the unhappy world where you just didn't get lucky. And you do the interest calculation before you made the raise, but it's fair. Right? What are we really worried about, though? Yeah.
You don't want half of the interest calculation to happen, and then the raise happens, and then the other half, or
right.
The other direction.
Yeah, so one way of saying that is like, this is copacetic, right? 1, 2, 3, 4.
Right.
And the intuition for why that's copacetic is because that's exactly the same as if T1 got a big lock and ran a completion before T2 began. We know that if you let things happen in the total order, totally, everything will be all right. It's also true that if we had, as we saw a moment ago, 1, 2, 3, 4, that would be okay, right? But like 1, 2, what's the bad one? So like 1, 2, 3, 4 would be okay. Because it would give you the same result if you had done 1, 2, 3, 4 at the end of the day, right? So think about that for a minute. This one is definitely not something that could happen if you got a big lock. These things are running concurrently in an interleaved way, almost stepping on each other's toes, but not, because we got lucky. So like that is okay. What's not okay? This is not okay, right? 1, 2, 3, 4. Because then X, Alice or whatever, would benefit from the interest calculation and Bob, Y, would not. So do you see? So there's a lot of different ways, now that we're doing compound actions, that the things can happen. Some of them are okay and some aren't. And there's this kind of intuition that the ones that are okay are the ones in which T runs to completion before T2 starts, or T runs to completion before T1 starts, what we might call the serial schedules. But they're not the only things that are okay. There are non-serial schedules that are okay, because they're going to turn out to be indistinguishable from the serial ones. So there's this gold standard of correctness for databases, which we're going to get to at the end, called serializability, that says, I ran in a chaotic concurrent way, but it's okay, because my run was equivalent in terms of its end state to runs in which there was no concurrency at all. In that sense, it does sound similar to our gold standard around replication and strong consistency. Like, if it looks like there was no replication, then your replication is strong. If it looks like there was no concurrency, then your isolation is strong. And then what does D mean? Durability, right? This is a topic that we talked about in this class, but not gone too deep on. Maybe I should take a moment and say a brief word about durability, like in the context of primary backup. So what do we think durability is? First, what's durability? Yeah.
Well, if the client issues an operation, then it better have gone through. If it were not to have gone through due to crash, then that means that the command was not durable.
Yeah, exactly. So I mean, typically we're a little bit more defensive than that. We say if a command succeeded, like in the sense that the client received acknowledgement or the commit went through, if you have some kind of acknowledgement from the system that it worked, then its effect should always be visible, even if there are crashes. So exactly what you said, except it would be unfair to say if I try to do something, it will always be durable, because it might just quit. But if I try to do something in the system that it worked, then any future state will reflect that, right? And so, for example, when you think about primary backup application, just for a minute, in the context of durability, even though we haven't talked about it, why does the primary wait the client comes in, does the thing? Why does the primary wait for responses from the backup? Is it to ensure strong consistency?
To ensure durability.
It's only to ensure durability, right? Because we were going to get strong consistency because of the total order decided by the primary based on arrival order anyway. If the primary just acknowledged the client right away, there wouldn't be any hazard of inconsistency. The hazard has to do with the fact that the primary acknowledged the client right away and then crashed, the data would be gone. And the reason we send the data to the backups is to ensure durability. But once we introduce backups, we become concerned about consistency, and we have to make a bunch of strict rules. Right, so I just wanted to bring that up, because durability is something that we've been sort of talking about softly for a long time, but never really looked at in detail and in the context of these protocols. Okay, so we have this intuition. Let's do some definitions. We're going to call a schedule and ordering over atomic operations. Okay, for example, what did I say? X plus equals 100. T1 says X plus equals 100. T1 says X plus equals X times whatever, 0.06. T2 says Y plus equals 100. T2 says Y plus equals Y times 0.006. So that is a schedule. It says that here are operations, here are the transactions that perform the operations, and in this schedule, this happened, then this happened, then this happened, and then this happened. Right? We saw how there's a great many schedules. Right? It's going to be like O factorial, where O is the number of operations, right? Does that make sense? That is a schedule. We say that two schedules are equivalent if it's going to turn out there's two definitions of equivalence. One is like the one that we want intuitively, and the other is the one that is slightly stricter, permits fewer schedules, but is computationally tractable. Okay, so let's talk first about the intuition. Like, when should you say that two orderings of atomic events are equivalent?
When the outcome is the same?
If they produce the same final database state. It depends what you mean by outcome, right? And what? So the database ends up in the same place. Values of X and Y are the same or whatever.
Ordering?
It's going to be and the values returned by reads from or query, the values returned are the same, right? Because the database doesn't just store data, it also sends data back to clients. And the union of what's in the database and everything that we output, that's anything that anybody can ever see. And like if two schedules are different, but they produce the same database state and they return the same values, if the tree fell in the forest, we wouldn't be able to tell the difference between the two schedules from the outside, right? So that seems like a very good definition of equivalence. This is called view equivalence. Now the problem with view equivalence is that in general in a database, we would want to determine if schedules were equivalent at runtime to decide which schedules to allow to proceed. And this problem, unfortunately, is NP hard. And sometimes the set of operations is big. So it's like NP hard with a big N. So we don't do this in practice. Instead, what we use is a stricter term, a concept called conflict equivalence. Okay, which says the conflicting operations of transactions occur in the same total order. Okay. It would appear that we need another definition. What the heck is a conflicting operation? Well, we talked about this actually a little bit in the context of rewrite storage systems. Anybody remember? We looked at three kinds of conflicts. The idea of a conflict is a pair of operations that the fact that they happen in a particular order matters with respect to what? Well, with respect to the final DB state or the values returned by reads. Right, so what were the three classes of conflicts we looked at?
Read, write, write,
No, we looked at write-write conflicts. And the intuition here is that, like, if the writes happened in this order, then the final database state reflects the value written by the second thing. And had they happened in the other order, something else would happen. Right? So obviously, these conflicts could cause two schedules to not be equivalent. Right? So we want to make sure that if transaction 1's write happened before transaction 2's write, we want to make sure that transaction 1's other operations happen before transaction 2's operations in this schedule. Right? And then we had write-read conflicts. Why is this a conflict? Remember, it's a conflict because if they'd happened in the other order, something different would have happened. Well, this is a conflict because if this happened, then R2 read the value that the, and remember, conflicts, there are these things on the same variable or row or same object, right? Then this read read the thing that this write wrote, and had they happened in the other order, it wouldn't have read that, it would have read something else, right? And then we would have run afoul of the value returned, right? And similarly, it's called an anti-dependency, where like you read and then I wrote, I stomped all over what you read, and that might have been different had the operations happened in another order, right? So what we want is to say schedules are equivalent if you can't tell the difference. it's going to turn out that if schedules are conflict equivalent, you can't tell the difference. So we got what we wanted. But there are going to be some view equivalent schedules that are not conflict equivalent. Which means there's some schedules that, using algorithms for conflict equivalence, we're going to throw away, say these are good, but they were good. And so there's opportunities for more concurrency parallelism if we did view equivalence. Except there isn't, because you can go dog slow. It's too hard to figure out things are view equivalent. Everybody follow that?
So we're choosing the harder thing because it's possible to compute.
It's not harder, it's stricter. In the same sense, right? That like, let's see. Here are the conflict equivalent schedules. Here are the view equivalent schedules. They admit a few more schedules. Admitting more schedules will be good. It's more flexibility. It's just that you might run forever trying to figure out two schedules are equivalent out here. So we do the computationally tractable thing, even though it means ruling out some possibly fine schedules. Okay. Okay. So we've got a definition of a schedule. And we've got a definition of what it means for two schedules to be equivalent in terms of like what we might like and what we can actually pay for. And so the only thing left to do, let's see, is to say what a serial schedule is. A serial schedule is a schedule in which each transaction completes all its operations before the next begins. Okay? So for example, this is a serial schedule. T1 does its thing, its first thing. T1 does its last thing. And then T2 does its first thing. And it does its last thing. And then T3 comes along. Right? This is a serial schedule. Right? Why is a serial schedule good? Well, because that's the gold standard, right? That's what it would have looked like if there was no concurrency. Nobody stomping on anybody else's values, right? And it's tempting to say, okay, well, I argued a moment ago that getting a total order over the operations can still run you into problems, as we saw, because like this total order was a bad one, right? But wait a minute, but if I got a total order at a coarser granularity, if I got a total order over the transactions, then it would be fine. Right, so why don't people just write databases, instead of doing all the crazy locking that we're going to learn about on Monday, why don't people just call out to an ordering oracle before submitting their transaction, get a number for the transaction, and have the damn database play the transactions in order? Right? Like, why are we doing all this crazy interweaving stuff?
To go faster.
Single point
It
failure.
sounds slow.
It sounds slow to do things in order. Why, though? Why would it be slow? Like, let's imagine a simple world where we don't even have any parallel resources. So if there's parallel resources, yeah, use for concurrency. Let's imagine it's just a single-threaded damn thing. Why would it be any slower to run all the transaction once things and then all the look, you have to run all the operations. And you got one thread. Why would it be any slower? It's going to turn out that it is, or at least in the past it has been. But why? Right? It doesn't seem intuitive. Yes?
Is this like with user interfaces, latency problems, blocking? You use concurrency even on a single core or to build a GUI?
That's good. Yeah, no, that's absolutely right. So, but in a database, obviously it's not think time of user that we're worried about introducing latency and blocking operations. What is it?
Not think time?
Yeah. I mean, you could imagine that some databases might be powering a GUI and there might be think time. But even if there's no GUI and it's all stored procedures and everything's just in-house.
Solving your client's computation based on the results you give.
Yeah, but if the client, if the client submits a complete transaction, waits for the results, their wait time is not impacting anything else, right? It would, so what else? So you're right. If these transactions are like so-called interactive transactions, where the client is doing reads and goes to the bathroom, yeah, sure. But even without that, we have issues in a database that will make a serial ordering slow, maybe.
Is it because we can't properly do pipelining if we're waiting for a full transaction to complete?
What do you mean by
before we start the next
pipelining?
one?
Well, like, if we're doing y plus equal to 100, we have to do a memory I/O, and during that time we could go and.
Well, good. That's the word I was looking for. I/O, right? Is that like at least in traditional disk systems, database systems, the data is stored on disk, right? Because there's more data than is going to fit in your memory. And that means that it takes like 2 orders of magnitude more time to read a value than it takes to like do some computation on the value. Like it's dog slow, measured in milliseconds, whereas your CPU operates in measured in nanoseconds, right? So what that means is that like you wouldn't want, like there's this opportunity for this I/O and this I/O to happen in parallel if you interleave the transactions, right? So the whole model of concurrency control involving interleaved operations of multiple transactions running in parallel and yet appearing to be serial, it really reflects a time that is mostly in the past when memory was expensive and small and the working sets of databases were on disk. And you had to hide the latency of going disk. And one of the only ways to hide that latency was to allow other transactions to come along and do reads and writes as long as they didn't conflict in the ways we already described with the running transaction. In modern database systems, particularly the so-called OLTP systems, they tend to fit their whole working set in main memory. And if they use their caches efficiently too, we don't have these massive latencies to hide behind. And the sort of value proposition of the complexity of what's called concurrency control, mechanisms to make sure that all executions are equivalent to some serial execution are costly and maybe unnecessary. And so there is a very famous system developed by Daniel Abadi and his team at Yale called Calvin, named after the philosopher who believed that everything was deterministic or whatever. And in Calvin, it works exactly that way. When a transaction comes in, the first thing it does is go to an oracle and get a number. All of the replicas run a single thread of computation, and they schedule transactions in the order of their numbers. And because they're running on main memory, there's essentially no delays. So there's no headline locking. Everything just runs at CPU speed. And so that works great. It's like a massive simplification. And this happens all the time in systems where you're like, performance characteristics of some of the hardware has changed. And so now we need to rethink designs. Or maybe we need to go back to designs that were popular 20 years ago and then weren't good anymore and now are like good again. And so like the big new thing, the big hotness that is happening now is byte addressable non-volatile memory. So it's like, holy crap, well, if you can put memory in your memory banks that you can use just like DRAM, and it's almost as fast as DRAM, but the data survives power cycles, maybe we should like rethink the way that kernels work. Maybe we should rethink the way that computation works. Because like now, like all data is persistent, and processes are these things that are much more short-lived than the data. Right? So there's all this neat work that's happening now. How do we rethink operating systems because this hardware has changed? And a lot of the time the answer is, we can go back in history and dust off old operating systems that people thought weren't viable anymore. Reconsider them in the light of new hardware trends. And this is happening in the database world too. So sorry for that tangent. Where was I? I still have to define serializability. Okay. Schedules in order of operations. Two schedules are equivalent if they leave the database in the same final state, and we have a cheap way of checking conservatively if that's true. A serial schedule is one in which each transaction completes before the next one begins. That's what we want. So yeah, there's only one thing left to say, and it kind of says itself, right? A schedule is serializable. What do you think? If what?
Indistinguishable from the serial schedule?
Please, the things that are in boxes only.
Equivalent.
Yeah, exactly. And we saw that, right? Because we saw how, I wish I hadn't erased it, we saw how that one schedule that looked like this was okay because it was equivalent to the schedule that looked like that. Whereas the schedule that went like that was not equivalent to any of the serial schedules. And we didn't care, this is really interesting, it's some serial schedule. We don't care which, because the serial schedules just could have happened even if there was no concurrency. So we just need to show that it's equivalent according to some definition of equivalence to some serial schedule. Is everybody with me? It's a lot of terminology, But I think it all makes sense when you stack up the terms in this way. So these are all terms we haven't seen before, but intuitions that, in some important sense, yeah. Okay, how much time is it? I went fast. Oh man, fast. I figured I'd be done. Okay, so maybe what we'll do is, usually we talk about properties in one class and mechanisms in the next. Since we have some time, we'll start to talk about mechanisms to ensure that all schedules are serializable. Yeah?
So how would I say the difference in saying a schedule is serializable if it's serializable?
Well, but saying it's serializable would be a tautology.
Yeah.
We can't define something in terms of itself, right? But we have a notion of what a serial schedule is that's clearly defined. A serial schedule is not the same as serializable, right? Because this was the only serial schedule that we looked at. T1, T1.1, T1.2, T2.1, T2.2. And this is the one that said T1.1 happened first, and then T2.1 happened, and then T1.2 happened, and then T2.2 happened. So this schedule is not a serial schedule. However, it's equivalent to a serial schedule. Why is it equivalent to a serial schedule? Because, let's see.
The results are the same at the end.
T1, let's see. These two operations conflict because they're writes on X. And these two operations conflict because they're writes on that. So we have two write-write conflicts. And in the serial schedule, T1,
You can't start T2 without T1 finishing, and you did.
oh, sure. Sure, I can start T2 without T1 finishing.
Not, it won't be serial.
It wouldn't be serial, right? But the point is, I guess the point I'm trying to make here is that the reason it turns out that we can prove that the schedule is serializable is that it conflicts on the same items in the same order as this one. Okay? So let's talk about how you could canonicalize that. It's a collection of algorithms, policies, and mechanisms that are known as concurrency control. I have a really, really, really awesome music video to share with you today. I'm not in it.
Oh.
No, but my former advisor is, and he's a musician, so it has real production values. Okay, so a concurrency control mechanism is a mechanism that ensures that unserializable schedules are prevented, either via making them wait or aborted. Make sure that unserializable schedules don't happen. And concurrency control, broadly speaking, is going to come in two forms. What you might call pessimistic concurrency control, which I like to equate with this, AKA, ask for permission, right? Mother, may I access this object? No, you may not. Someone has already accessed it. You might conflict with them. And optimistic. AKA, ask for forgiveness or YOLO. How do you imagine these two mechanisms playing out? How would you implement, not that there's only one way, but how would you implement